Okay, so you can probably see on the website that I decided to spend more time on gauging variance. And now there is I turned it into a whole section. So we're going to spend 2 or 3 lectures on gauging variance. So today we're going to start part 4 of our quantum field theory course, still talking about classical field theory. And we're going to be talking about gauge redundancies. So a little bit of review of where we stand in this course so far. We talked about, in part 2 and part 3, we talked about the principle of locality and principle of symmetry. And then in part 3, we discussed this triangle connection between differentiable symmetries of the action. Actually, sorry, I always forget to do this. Oops. Okay. Yeah, we talked about the differentiable symmetries of the action, and we said that Noether's first theorem gives us conserved charges. And then we also said that every time you have a bunch of symmetries, they form a group, and the group you could represent it either in the field space or in the Hilbert space. And then in the case of Hilbert space representation, we said that the representation has to be unitary or anti-unitary, and that was the well-celebrated Wigner's theorem. Then finally, last lecture, we said, we said also that differentiable symmetries are Lie algebras and Lie groups. And in the last lecture, we said that conserved charges that you construct using Noether's theorem are going to satisfy the Lie algebra. So in the case of Poisson bracket, it's something that you're going to work out in an exam, in a homework. I will try to post the homework today, but in case I don't get there, it might be in a day or two. So they satisfy the Lie algebra. We talked about central extension, and we said that when the Lie algebra is semi-simple, identity is not one of the generators of the Lie algebra, therefore we cannot centrally extend it. Central extensions had to do with this possibility in quantum mechanics that we have projective representations and not just representations, with this extra phase that was implemented into multiplication of matrices in the representation. And there was freedom over there because in quantum mechanics, the global phase won't matter. It's not observable. All right. So in part 4, so that was the story so far. In part 4, we're going to start talking about gauge redundancies. So what is this? I started by telling you guys that we have been modeling nature using local quantum field theories, local field theories, and this has been extremely successful. And that just points to the fact that nature is local. However, there are lots of theories out there in nature, actually the whole standard model is like that, where the theory is local, modulo some subtlety. There is a very special, limited, and a special form of non-locality that is topological. So we're going to explain that. I decided to spend some lectures explaining that. There's a very specific form of non-locality, topological non-locality, and these theories are called gauge theories. They're still local, as long as your topology is nice, flat, like flat space-time, it all looks local and nice. But the moment you have some sort of a funky topology, there will be non-localities coming in. And then the whole story of gauge redundance comes in when you insist on writing a local action for these gauge theories, right? So the terminology that has been used in the past has been, people call gauge theories gauge symmetries. People used to call them local symmetries. We're going to explain that today. But the modern terminology is gauge transformations are redundancies of the description. There is no symmetry as the same way that we discussed in the previous lectures. There is something called higher form symmetry, in particular one form symmetry. which is related to the fact that this form of non-locality is topological. So I wasn't gonna discuss this, but I decided that I should probably throw in some more modern perspectives in this course. That's why we have this extra lecture. All right. So today, what are we gonna say? We're gonna talk about, so by the end of the lecture, hopefully you'll have the answer to these 4 questions. What are gauge redundancies? How are they related to locality? We already, I already briefly mentioned this in one of the lectures when we discussed overviewing electrodynamics. Why are they called, or they used to be called, local symmetries? So hopefully that will become clear as well. This is something that I will encourage you guys not to use. The terminology I would encourage you guys not to use, but if you're reading old papers or talking to someone who is a little bit more old school, you will hear the terminology. And what is the action of a non-abelian gauge theory? That's called the Yang-Mills theory. So that will be very important because, as we'll say in the last slide of this lecture, all forces of nature in standard model, electrodynamics, weak nuclear force, and strong nuclear force are going to be gauge theories. They're going to be non-abelian, well, electrodynamics is abelian, but the other two are non-abelian. Those are the theories of QCD and electroweak, and they're all Yang-Mills theories. So this action we're going to work towards at this lecture is going to contain the description of all forces of standard model. All right. Okay. Any questions about where we're going with this? Any questions about previous lectures?
Whether a gauge theory is abelian or non-abelian, is that determined by the commutativity of the group?
Yeah. So we define what a group. When we talked when we discussed groups, there was a multiplication. If the multiplication is commutative or abelian, we say it's an abelian group. If it's non-commutative, it's non-abelian, right? So simplest example of a Lie group that is non-commutative is SU2. And then what's the next the other easy example you can imagine? So the simplest example of Lie algebra you can think of is U1, pretty much, right? That is going to be realized as a theory of photons. The next simplest thing you can imagine that's non-commutative is SU2. That is the theory of electroweak. The next easiest thing is SU3, that's chromodynamics. So that's the theory of strong force. So that's just how things go.
Thank you.
Sure. All right. Now let's start with electromagnetism as a U1 gauge theory, right? So we went through electrodynamics. I did a review a few lectures back, but I decided to go over it again, pointing out some certain things for you guys to look up. So we said that in we won't have time to discuss them in detail, but I just want you guys to point you guys towards where you should think, how you should be thinking about this. So we saw that in electrodynamics, the physical degrees of freedom were the magnetic and the electric fields, vector fields, that we packaged into the field strength. And then I said that these are the physical degrees of freedom, right? But we often use a gauge field, a gauge vector field, which has the time component of this is electric potential, and then the spatial component of it is electric vector potential, is a vector potential. And I said that we do this because we insist on local action. The physics is described with F mu nu, electric and magnetic field, and there's no physics associated with the potentials. It's a redundancy that we use to insist on locality. So that was originally my plan to go with this message for the whole course, but I decided that it's time for you guys to give you a little bit of modern perspective. That is a little bit more nuanced. So there is a place you could have complained in that lecture where you have learned in the past where there is some physics associated with potentials and not forces. That is the Aharonov-Bohm effect. So read it on Wikipedia, remind yourself of what it is in quantum mechanics. You're probably learning advanced quantum mechanics, maybe quantum mechanics. It's a physical phenomena where you end up picking a phase that's observable due to the propagation of a particle in a region of space where the potential, the vector potential is non-zero. However, the fields are zero. Right? So I'm just summarizing for you what the phenomenon is. Historically, Aharonov and Bohm came up with a particular setup, but that's what the phenomenon is. You could come up with setups where you will end up with an observable in quantum mechanics, a phase difference that is associated with a region of space where the potential is fixed, non-zero, but because the potential has no gradients, it means that the electric and magnetic field are zero, right? So how are we going to interpret that? This suggests that there is more to the electrodynamics than the electric and the magnetic field. So classically, there are two ways to go about doing this. There are two options. You could say that you're going to insist on the electromagnetic field, electric and magnetic field vectors as your physical degrees of freedom, and call this Aharonov-Bohm effect or these kind of things as some sort of non-local effects. Why? Because if your electric potential or magnetic potential is non-zero at a point, it means that somewhere else in space there are some charges. Because Stokes' theorem, you could use Stokes' theorem to write down the electric potential or magnetic potential, electric vector potential, vector potential at any point in terms of all charges in space. So here, you could insist on E and B being the physical degrees of freedom, but having a source of non-locality. Because the physics in this region where the particle is propagating depends on some other charged particles that are in remote regions. Right? That is what is meant by non-locality. I'll come back to this. This is the old perspective. I'll come back to this and I'll actually clarify this a little bit more when we discuss topology. But that's one perspective. It's legit. The other perspective, from the point of view of classical theory, is to just accept A mu, the vector potential, as your field degrees of freedom. However, keep in mind that there are a bunch of gauge transformations that are redundant. They're not real. They leave the action invariant, but it's not a real symmetry. It's simply a redundancy we've introduced because we want to insist on the locality. Formula in terms of A mu, everything is local. Any questions about this? This is one of the main messages that I want to send across. So in the remainder of this lecture, I'll adopt the second, I'll adopt the second point of view, working with A mu, right? I'll pretend that this is the degree of freedom, and then there will be gauge transformations of A mu, they'll call redundancies. Good. So in summary, I want you guys to have in mind the following picture. I haven't talked about topology yet. The following picture, that electrodynamics was showing some sort of non-local behavior. We decided to insist on keeping locality as a basic principle at the cost of introducing some redundancies. And we're okay as long as we always keep track of these redundancies and make sure we don't confuse ourselves. Are we good? Any questions?
Why is using potential more local than using field?
Because I can write down a local action, meaning that an action which is an integral Lagrangian. Now, if you try to do the same thing with E and B, you fail to do that. So this is, if you recall, so F mu nu is written in terms of E and B, that's fine. But when how do you couple the charges? You have to write A mu J mu. That term you cannot write in terms of E and B's. And that is precisely the core of this Aharonov-Bohm effect. If in the Lagrangian you could just write something in terms of E and B coupled to currents, then everything would have been fine.
All right.
Good? Yeah. And any other questions? All right. So To get the terminology straight, recall we had symmetries that we discussed so far. We had global symmetries. These have to do with internal transformations, right? And then we had space-time symmetries. Noether's first theorem told us that when we have differentiable symmetries, you're going to end up with conserved charges, conserved currents. So there are observable consequences to symmetries in nature, and there are charges that are observable and we measure them and they're conserved. So if we make up some sort of a like imaginary made up symmetry, gauge symmetry, there should be no observable consequences as long as there are no issues regarding this like topology or this Aharonov-Bohm effect. As long as we're doing standard things, there should be no consequences. So in the old terminology, gauge theory was called sometimes local symmetry. I'll explain that. And it was called gauge symmetry. This is old terminology. In the modern terminology, we talk about higher form symmetries, in particular one form. So gauge theory that we're going to discuss is one form symmetry. And then we talk about gauge invariance. Is it all good? All right. So now, because it's a little bit of a loaded question, you guys probably don't know, you might or might not know topology very well. I'm not going to bombard you with math. I'm going to give you explanations for why we introduce gauge redundancies at various levels as we go ahead. So I gave you already a hint from Aharonov-Bohm effect. Now I'm going to give you another hint. So this hint is perhaps even more physical. This is perhaps the most direct way of saying why we introduce gauge redundancies. So I want to summarize the reason with 2 points. The first one is what we are dealing with is a massless spin 1 particle. Photon is a spin 1 particle. That's massless. The fact that it's massless, it tells you that there are only 2 polarizations that are transverse. However, in the next section of the book, this course, we're going to see that if you have a spin 1 particle that's massive, you're going to end up with 3 polarizations, right? So the issue is this: if you try to describe a photon as a spin 1 particle, the way that you would normally do using a local action, you've introduced one extra polarization that's unphysical. And that is the longitudinal polarization. So now I invite you guys to think about why can't photon oscillate in the longitudinal direction? And here's a hint. The velocity is d omega dk. Just think about that. Why can't photons have a longitudinal polarization? And I already gave you a clue. It has to do with the fact that it's massless. So it travels at the speed of light. So gauge invariance is important because you have to kill this longitudinal mode that you introduced by hand. It's not there. It's non-physical. Another side comment for you guys to think about is that, well, there is a spin 2 particle that's massless. It's called graviton. If you insist on writing a local, it's sort of similar. If you insist on writing local action for it, you're going to introduce a whole bunch of extra polarizations that graviton doesn't have. So maybe, so here's something for you guys to think about. Maybe gravity is also very similar to gauge theory. So you have to introduce some sort of fiducial transformations to kill these extra degrees of freedom, these polarizations. It's just something for you guys to think about, okay? We're not going to be talking about the gravity in this course, but sometimes there's a perfect moment for me to throw out something for those of you guys who are interested. All right. So that's point number 1, right? The reason we introduce gauge redundancies at the core of it is the fact that photon travels at the speed of light. It's massless. It's massless, therefore it travels at the speed of light. Therefore, it should have 2 polarizations. Whereas if I write down naively a local Lagrangian for a spin 1 particle, no matter what the mass is, there will be 3 polarizations. One of those is extra, it's junk, I've introduced it by hand, it's redundant. This issue of polarization will become hopefully clear when we talk about in the next section of the course, when we talk about the Poincare transformations and the representation theory. Second reason is what I already told you. The physical electromagnetic fields is not all contained in F mu. As I tried to demonstrate it or point out by the Aharonov-Bohm effect, or you could just say that as we in the maybe 2 lectures from now or next lecture, we're going to mention that gauge theories have some non-local observables that are topological. They are Wilson loops. They are only there when the topology is non-trivial. So there's some form of non-locality that's intimately tied to topology. So that's another reason, but this is a little bit more advanced and it's a little bit more remote at the moment to see the connection to local action. All right. So are there any questions about why we introduce gauge redundancies? We are insisting on a local formalism for a theory that has some mild form of non-locality, very tamed and mild form of non-locality. One manifestation of all of this is the fact that photon is massless and spin 1. Any questions? All right. These observables are going to be called Wilson loops. If you do know about them already, these are the observables that are non-local. Now, why is gauge invariance sometimes called local symmetry? Okay. So what were symmetries? These were transformations that were leaving the action invariant. These redundancies that we introduced also leave the action invariant, simply because we use too many degrees of freedom. But there is a difference between the two. In symmetry transformations, whether it was internal, that we call the global symmetry, or space-time, that we call the space-time symmetries, phi prime, let's say, is, oh, sorry, whoops. Whoops, I wrote this up. This should be down here. This is space-time transformation. And then, yep. So an internal transformation is like this, right? But importantly, the transformation matrix, so the transformation occurs that the transformation matrix, the representation is independent of the point, right? So it's something that occurs at every point in space. Just recall what Ising model is. Ising model is a bunch of spins. The Hamiltonian is D2 symmetric, which means that at every point in space, if you take a spin and flip it down, but you have to do it at all the spins all at the same time, right? If you do that, that's a symmetry. The transformation has to be applied at every point, independent of the point, and it should be the same way. That's a symmetry of the action, the Hamiltonian, right? These are internal symmetries. These are global symmetries. They act at every point, independent of the point. Now, space-time transformations are a little bit different, right? So for example, if you had a scalar field, you basically phi prime of x prime is phi of x mu, but x prime is again transforming with, let's say if this is a Lorentz transformation, with lambda of mu nu that is independent of x, right? You are boosting or translating or rotating all points in space the same way. If you take a picture, if you take your space and rotate at one point and not the rest of the points, you're going to end up with something messed up, right? So that's not a symmetry of the action at all. All points should be rotated the same way by the same amount, independent of the point. Good. All right. And then we mentioned that fields with spin would necessarily, if you were talking about space-time transformation, not only you will have to transform the point, but also it will come with an internal transformation in the field space. And that's a representation of the Poincare, the Lorentz transformation. Or we're going to get back in the next part. But the story is no different. The transformation inside the field space or in space-time is independent of the point. These are the symmetries we've been discussing all along. So if we are talking about to clean up the discussion, let's forget about space-time transformation for the rest of this lecture and focus on global symmetries. All right? So these are internal transformations. So phi prime of x is some u acting on phi of x. And u is independent of x, right? And then we saw that our Lagrangian is invariant under this. For example, if you write that del mu of phi, this is invariant because hopefully this matrix notation is clear. Is the matrix notation clear? Maybe I should just put indices A, B, B, right? A, right?
Shouldn't phi A, for instance, be dagger?
So I didn't say unitary representation. That's why I wrote u minus 1.
Okay. I'm talking about
the notation of u as a representation, but I didn't mean a unitary.
No, I'm talking about the field, like in the Lagrangian. One of them, shouldn't it be, I mean, the complex conjugate at least? Or
oh, yeah, you're talking about this guy.
Yes.
No, not necessarily. If this is an orthogonal group.
Okay, sure.
Okay, sorry. That all of that is in this index, upper and lower index.
Okay, got it. Okay.
Yeah, this is an issue of representation. Yeah, this is I'm using a compact notation.
Yeah.
Could be, yeah. All right, good question. Thank you. So this is what the sort of global symmetry was, but it turns out in trying to write down a Lagrangian for gauge theories, you end up with an action that will show a symmetry where the symmetry transformation depends on the point. That is the origin of the old terminology of a local symmetry. When people modeled this, they wrote down an action for electrodynamics. They realized that it now has this enhanced fake symmetry, if you wish, because they introduced too many variables. There's this fake enhanced symmetry, which is kind of bizarre. It's true for transformations that can act differently at different points. So let's see how that works. So I'm again dropping all the indices. But now there's a problem with this. The problem is that, okay, when you transform like this, you want your Lagrangian density to be invariant, but it's no longer going to be invariant because del mu of phi, there will be u sitting in here, and if you take derivatives, the first term transforms the way you expect it to transform, right, covariantly, but the second term, there is this extra junk that you get. There is this inhomogeneous term, this extra junk that you get. Therefore, del mu phi is no longer invariant. So this was something that people, you see, this was like, I don't know, it's a post-discovery in a sense. People knew about electrodynamics, people had written down Maxwell equations, they were just trying to write down an action that was local. And then they realized that if they have a charged particle, right, and if they just promote global symmetry to some sort of local symmetry, they're going to end up with such a setup. Okay. So what is the symmetry transformation we're talking about? In U1 gauge theory, this is just U of x is e to the power of I alpha of x, right? We're talking in U1 gauge theory, your charge fields are going to be complex vector fields. We gave an example of this in the past, right? So remember the U1 global theory, complex scalars? It's the same theory where the rotations were e to the power of I alpha, and I've promoted alpha to a function of space. So del mu of phi now transfers in this way. with this extra term, right? And if we want to somehow forcefully make it invariant, we need a new type of derivative. We need a type of derivative that transforms nicely. It's called covariantly. Hopefully the term covariant is familiar, why I'm calling it covariant, right? So it's called covariant derivative. In the next lecture, I'll come back and explain actually where are these coming from. At the moment, let's just say it's a guess. It's just something we throw out to come up with a theory that has a quote-unquote local symmetry, right? In the next lecture, I'll actually explain the origin of all of this. It's very, very natural. 2 lectures from now, we'll see that actually why you should expect this from the point of view of lattice models as well. But so you define something called covariant derivative, this capital D mu, which is del mu phi plus I e a mu x phi of x. This is a vector field. Sorry, we're going to see in a second it's a vector field. It's a gauge field you've introduced, and E is the charge of the field phi. So now, if you just repeat the exercise before, you previously had this term, now you get this extra term. If you want to ensure that d mu, this covariant derivative, transforms covariantly, a mu should transform in the following way, so that this term vanishes, right? That's the goal. And then if this term vanishes, d mu, the covariant derivative squared is a legitimate kinetic term that's going to be invariant under this quote-unquote local symmetry, right? So we're just cooking up a theory that has local symmetry. Now you realize quickly that this transformation implies that a mu of x is a Lorentz vector field associated with spin 1 particle. So if you go back to where we're discussing the transformation of the spin 1 particles, this is what you discovered. So it's important to zoom out for a second and see what are we doing. We started with a theory of pure charged particles, just a bunch of particles, right? Just no photons at all, right? We just had a bunch of particles. Then we demanded the theory, so say it had U1 symmetry. We demanded that the symmetry is local. And then we learned that that comes at the cost of introducing a new vector field. We were forced to introduce a new vector field to arrange for this local symmetry. Local symmetry is a form of non-locality already. Because if I rotate if I had a spin model and I was rotating this, flipping these guys with a certain, like doing a flip here and a different flip really far apart, outside of the light cone of this, space like separated from this, the theory should know that it should remain symmetric. It's a form of non-locality. All right, but this is the action that you would want. Now, this generalizes easily to non-abelian gauge theory. So you could imagine instead of U1, you have UN, where your field is a complex vector field. And the fundamental representation of, when I say vector, I mean fundamental vector respect to UN, right? And these UXs are n by n unitary matrices. Now your covariant derivative, these are now matrix valued things, is identity, because it's a matrix valued, del mu minus IG. G is the analog of charge for this non-abelian theory, a mu of x, where a mu of x is now a matrix valued field. It transforms in a representation of UN. Under such an assumption, del mu of you want the covariant derivative that you just defined above to transform covariantly. And as we just saw, the way to arrange for it is a cancellation. You just repeat this example we did over here for the non-abelian case, and you learn that a mu should transform in the following way. it should be multiplied because our u's, remember, I just started by assuming that u is fundamental field, vector field u, phi's are in the fundamental representation. So these u's are fundamental representation of the group. A mu is transforming using u of x on the left and u minus 1 on the right, fundamental and anti-fundamental. And this is the adjoint representation, if you recall from the last lecture. There is this inhomogeneous term there, and that inhomogeneous term is inevitable. It's just a vector field. So A mu of x is in the adjoint representation. Any questions so far? I haven't connected this with electrodynamics yet, right? So just to summarize, what we did was that I first motivated electrodynamics. I said there is this non-locality that want to insist on local description. We introduce a potential, vector potential, these redundancies. Now, I wanted to explain, I switched gears and I wanted to explain why this is called sometimes local symmetry. So I said, let's start with a theory that has a global U1 or some global symmetry. Now let's demand is actually symmetric under local transformations that depend on space. And you will see in a second that this is going to become gauge theory. This is going to become QED, or sorry, electrodynamics, electromagnetism. But for now, I'm just explaining what if you wanted to have a theory that had local symmetry, right? It just, if you want to arrange for that, you should promote your derivatives to covariant derivatives. And then when you do that, there is this gauge field that's introduced. It's a vector field that transforms in the adjoint of the representation. In this example. Any questions? All right, so let's work out an example. Let's take the simplest example we can, SU2, right? Just to familiarize ourselves with matrices and the fact, use all the jargon of technology of Lie algebra that we learned in the last lecture. So the adjoint representation of SU2 is written is given using the Pauli matrices, right? It's three-dimensional. Actually, sorry, what am I saying? No, that's right, that's right. So your vector field is going to be expanded in the following form in terms of the three Pauli matrices. And this extra, I might be messing up factors of half, but here I'm writing it down explicitly to see that it's a vector. It's a 2x2 complex vector, right? So more generally, if you have a group that is dimension D, A mu, because it's an adjoint, is going to have you can think of the adjoint always in terms of the fundamental, anti-fundamental. So there will be the fundamental index up here, anti-fundamental down here, right? And you could expand it in terms of because the dimension of the adjoint representation is the same thing as the dimension of the group. It's just basically can expand it in terms of the generators of the Lie algebra, right? So now if you make an infinitesimal transformation, you're going to get delta AB plus this. Now notice that by making this symmetry local, previously we had theta k's, now these theta k's become theta k of x, right? Because at different points, you're doing different transformations and you're requiring this to be a symmetry, right? So then delta phi of x is going to be this way. This is the variation of the field as expected. And you will get a symmetry if your delta A mu of k, which is k is the index that labels the representation, the generator of the Lie algebra, as in the following form: I theta lk, I theta lx. This is x dependent. Here is the gauge field, right? How it's transforming, and these are the structure constants of the Lie algebra. In the adjoint representations, these are just generators, right? The adjoint representation, one other way of defining it was that when you use the generators, when you use the structure constants of the generators, right? And then there's this extra term is out there because theta does depend on x. This is that inhomogeneous term that we have. Sorry. All right. So putting all of this together, what did we do? We generalized. We can now write down a gauge invariant action for a free scalar field in representation R of a gauge group G. So we write down an action for a free scalar field that has a U1. Oh, sorry, has a group G, non-abelian general non-abelian group G, local symmetry, and the action should look like this, right? Here is the free term, right? Written in terms of covariant derivative, and the potential, it will be just fine as long as you just sum over all the generators, because the fields are labeled by the generators of the Lie algebra. You could check explicitly that this is a local symmetry transformation. This is invariant on the local symmetries. So in your homework, originally I wanted to have it as a discussion in the course, but I decided to push it to the homework. You will apply Noether's theorem to gauge theories, to local symmetries, and you will discover something funky. So I'm just going to tell you what you're going to discover, but in your homework, you're going to work it out. You will find that your charges, this is called, actually, the content of this is Noether's second theorem. You will discover that in the case of global symmetries, our chart, what did we have? We found that we had this conserved current that we integrated, this is time and this is space. We integrate, because we define the charge by integrating overall space, right, at a fixed time. So Q of some time, final time, right, some final time as integral over space at time t of f of charge density J0, right? And it's equal to the integral over here. When I discussed this, nobody complained, because this is not what you see in electrodynamics. In electrodynamics and electromagnetism, one of the very first courses that you took in first year of undergrad, you learned that the electric charge is not an integral over the whole space, but it's actually an integral on a ball codimension 2 surface, some surface at some ball at some finite radius. You're not, to calculate the electric charge, you're not integrating over the whole space. You're only calculating, you're writing in an integral over some region, some sphere or something. And that represents all the charge inside it. Now, if you call from Stokes' theorem, this is in piece with Noether's theorem if the current that you get, if the charge density that you get is actually also complete derivative. So this is going to be something that you'll work out in your homework and you'll see. So this is one key distinction between global symmetries and gauge theory. All right. Any questions? Okay. Now, if you recall, now I want to connect the two stories. If you recall, I said in the past when we wrote down the local action for electrodynamics, the term that we wrote was this. This is the term we wrote, right? Integral of F mu nu, F mu nu. Now, how is this related to covariant derivative and local symmetries? The answer is very simple. Local field strength could be understood as 1 over minus I E is the charge, it's just normalization of the commutator of the covariant derivative. This equation is the key relation between local symmetries, quote unquote local symmetries, and the gauge invariance. right? So the gauge invariant term that we wrote for QED, for electrodynamics, is actually nothing but the commutator of this covariant derivative we just defined. So how do you see that? What does it mean to talk about covariant derivatives of this? So take a field phi and apply this. This d mu is this. So these are the two covariant derivatives you want to make, calculate, right? So you expand this commutator. We're doing classical physics. Hopefully this is clear. We're still doing classical physics. The only reason that I mentioned the term commutator is that I have derivatives, right? Del x and f of x do not commute. Hopefully that's clear. So if you expand this commutator, you're going to get the commutator of del mu phi mu, which classically is 0. Then you get the commutator of a mu and a nu, which classically is 0. In quantum mechanics, it won't be 0, right? And well, might or might not. We haven't discussed that yet. Then you get this extra term. If you just work it out, you learn that this is minus IE del mu a mu, the anti-symmetrized field strength. So this equation is the key idea behind Yang-Mills theory in a sense, right? So Yang-Mills theory tries to relate the formulation of gauge theories to something more fundamental that could be generalized. So in the case of electrodynamics, electromagnetism, we just guessed, right? F mu nu, we wrote down F mu nu. It was a tensor that was written only in terms of E and B, and then we wrote F mu nu, and it was the right thing that under variational principle was generating Maxwell equations, right? So the question is, how do you Yang-Mills? The story of this theory is that how do you go about generalizing electrodynamics to cases where the gauge symmetry is non-abelian? The route is through local symmetries that I just went through. So you first define covariant derivative. In the next lecture, we'll tell you actually what's the physics of covariant, what's the mathematics, what's the geometry of covariant derivative. There's a beautiful geometric picture behind this that you could have, if you knew enough math, you could have guessed from day one. But the idea is that the covariant derivative is this thing that you introduced because by hand requiring to have a local symmetry, then F mu nu comes out as the commutator of the covariant derivative. That first of all, covariant derivative introduces a gauge field, right? And then F mu nu comes out of that. So in the non-abelian case, a generalization will be straightforward. You would say that F mu, you just define non-abelian field strength to be 1 over minus IG. G is a coupling, right? Or charge. The coupling, the commutator of the covariant derivative that's non-abelian. Now, recall that these covariant derivatives are now matrices, right? These are matrices in transforming. So these are matrix valued field. This is a matrix valued field strength, right? So how do you do it? Well, luckily covariant derivatives so how does F mu transform under gauge transformation? Luckily, we cooked up covariant derivatives so that they transform covariantly under gauge transformation. So this is how they transform. If you trace it back, go through the algebra, you learn that F mu nu transforms in the adjoint representation, but this time covariantly. This is crucially different from electrodynamics, where F mu nu was gauge invariant. Field strength of electrodynamics was gauge invariant. Once we generalize it to a non-abelian thing, what we found is that the closest thing that deserves to be called field strength is transforms covariantly in the adjoint representation of the gauge group. Therefore, it's unphysical. Anything, we just said gauge transformations are unphysical and man-made, right? They're just made up. Anything that transforms under these transformations cannot be physical. Has some unphysical things at the very least. So this is not good enough. We have to build out of this a Lagrangian density. Well, Lagrangian density is a number. This is a matrix. The solution is simple. You need to take a trace of some sort. So in some representation R, if you have your generators of your Lie algebra lambda k and lambda l, the trace of it is that we diagonalize them, we make them orthonormal, right? We often make the generators of the Lie algebra orthonormal, and then the coefficient we put here is often called the quadratic Casimir, right? In the trivial representation, the quadratic Casimir is 0, sorry. Right? In the 0 or 1? I'm kind of confused. Sorry, I'm being slow. Yeah, it's 0. Yeah, of course it's 0. Yeah. In the fundamental representation, I told you that we often normalize using coefficient half, right? That's just convention. It's convenient. But in general, there will be something that's called quadratic Casimir. So now we're ready to write down the action for non-abelian gauge theory. The action is going to be the trace of F mu nu, F mu nu. These are matrices, representation matrices. And to properly normalize it, I'm going to divide it by T of R, this quadratic Casimir, so that nobody ever worries about normalization, right? This way, I just make it independent of your choice of normalization and my choice of normalization, right? Is this action clear? This is called the Yang-Mills Lagrangian. So was there? Yeah.
Where does the 1/4 come from?
Oh, that's another conventional thing. So actually, I had the 1/1/4 in electrodynamics as well. So it comes from this. I went through this in one of the lectures. If you recall, for scalar field, we normalize by half, right? Because it's phi squared, and you take a derivative with respect to phi, so you get the term that shows up in the equations of motion is linear, right? The two cancels it here. Why did I do this? Why did I normalize by 4 in the case of gauge theories? Because F mu nu is anti-symmetric. As you sum over mu and nu, you're doing it twice, right? Because 0 and I and 0 appear. So this 2 is to cancel that 2. We already had a 2 originally. There's an extra factor of 2. Here's 1/4. Any other questions? You will see various ways of normalizing the action. People sometimes put G squared down there, depending on how you are, the theory, the setup you're considering, it might be sometimes more convenient to use a different notation convention. Any other questions? It's an important moment to pause and think about all the steps we went through. So I want to summarize. I started by saying that gauge theories are these theories that have some mild form of non-locality. And I gave as example Aharonov-Bohm effect in electrodynamics. And also I gave an example, well, I just mentioned it, I didn't quite say it, this topological thing that we're going to get to. But more clearly, the need for such a thing is urgent from the very fact that a theory of electrodynamics is supposed to model photons. Photons are spin one particle with 2 transverse polarizations. Now, spin one particle, canonic, the standard action, local action you write for it has 3 polarizations, 2 transverse and 1 longitudinal. Photon cannot have a longitudinal polarization. I pose it as a question for you guys to think about, but it's simply because of the fact that it's traveling at the speed of light. It's massless, right? If photon had a mass, it would have had another degree of freedom. That's very dramatic. So if photon, this is very crucial. If photon had a teeny tiny mass, actually, here's the question. Is it possible that photon has a teeny tiny mass that we've never observed? The universe would have looked very, very different. Because it's not just a tiny mass that we haven't seen yet. It's actually an extra degree of freedom. There will be a brand new polarization in light that would change things dramatically. It's one of the reasons that well, another thing, could photon be massive? Sorry, if you add a mass term for the photon, what does it look like? You would write m squared a mu, I imagine, as a term in the Lagrangian. Is that term gauge invariant? It's not. So gauge invariant forces the carrier of the gauge boson, the carrier of the field, the quanta of the gauge field to be massless. And it's crucial that it's exactly massless. So if it had a teeny tiny mass, we were not talking about the redundancy of the description, we're talking about an actual symmetry. These are very important, right? So these are dramatic. But I want to make that point very clear. Okay, so that was the story, that motivation for gauge fields. Then I said that historically, gauge theory has been called local symmetries, a theory of local symmetry, and I wanted to explain that. So I started by saying that assume that we wanted to write down a theory that has a local symmetry. For example, we took an example of a complex scalar field and promoted the U1 symmetry of it to a local U1 symmetry, e to the power of I alpha of x. We saw that for this to work, we had to come up with a brand new form of derivative we call covariant derivative that has in it a brand new vector field degree of freedom called a gauge field, right? And then because it's a vector field, it transforms nicely enough that this cancels and you can write down a nice action, which is invariant, right? Because the covariant derivative transforms covariant. Now, this gave us a principle for the connection with electrodynamics came through the fact that the commutator of two covariant derivatives was F mu nu, was the field strength. This allowed us to connect the two formula of them. Then Li and Yang took this, I don't know historically actually how it worked, but they took this and let's just say imaginary world. They ran with this and they said, okay, now that I understand I can formulate, write down an action principle based on covariant derivatives, let's formulate a covariant derivative for local non-abelian symmetries. We saw that you get a field strength out of it, which is not gauge invariant. It's only gauge invariant in abelian cases. In non-abelian cases, gauge covariant, so it's unphysical. However, F mu nu squared, F mu nu, as matrices, you multiply them, you have to take a trace in the representation. That beast is gauge invariant. That was the action that they suggested. It's called the Yang-Mills theory. Of course, I'll say in a slide that this is actually the theory that describes nature. But let me point out something very, very crucial. If you take this action and expand it in terms of the Lie algebra generators, it's going to look like this. So I've already done some simplification. These are the components of the field strength in the direction of any of the generators. This is the action that you often see right there. Now, what was F mu nu k? It was, if you just write it explicitly, it looks like this bit. This looks like the abelian term, but it has this extra term, which is second order. So if my Lagrangian is second order, has a second order term in F mu nu, has second order term in A, and the Lagrangian is second order in F mu nu, my Lagrangian is fourth order in A mu nu. Actually, if you expand it, you're going to have third order and fourth order. That means interactions. That's a non-Gaussian theory. Why? Take this Lagrangian, one more question. Vary with respect to A mu, you're going to get terms that are non-linear. You're going to get a quadratic term, as a force, and you're going to get a quartic term. This means that non-abelian gauge theories gauge particles. The quanta of non-abelian gauge theories are going to self-interact. Photons, in the case of photons, we were lucky that they didn't self-interact because the theory was abelian, right? These terms were zero. Recall that these are structure constants of the theory. They're Lie algebra. In an abelian theory, that those are zero, therefore there are no self-interactions, right? Photons do not self-interact. However, in SU2, the gauge bosons will self-interact. These are the very well-known W plus minus and Z bosons. These are particles that we have discovered in nature. They interact, and their interactions are precisely described by these terms. So that's one good reason to go learn about the SU2 representation theory, because it tells you what's the form of the interaction of W and Z bosons. You have to care about it if you're a physicist. Gluons also self-interact. That's the theory of SU3. Now, a comment, because we have a few minutes, a comment for you guys to think about. For those of you guys who care about quantum mechanics, this is something that really blows my mind to this day. The very fact that photons are massless is massless modes. Massless modes in quantum world means a perfect messenger. Some interaction happens, there will be some remnant, there's some sort of collision, something happens, then photons are produced. These photons start propagating, and until they reach your eye, they're not going to get messed up. Because photons don't self-interact. So they carry the messages they record perfectly. This is why we can look at the night sky and know exactly what happened. Because in between some far remote galaxy and you, there are no atoms. Photons interact with atoms. It's just vacuum. Right? So photons, they record some event and they just come and perfectly transfer it to you. If photons self-interacted, you would have never been able to look at the sky and see any, well, the world would have looked horribly quantum mechanical. Horrible quantum mechanical. Well, first of all, if they had math, because it's a gauge field, the absence of mass is tied to the fact that it's not self-interacting, right? But if it had mass, it would just decay, so it won't travel very far. But even if it did, it could self-interact, right? So the fact that we have a massless gauge boson around photon is a lucky phenomenon. It's very, very lucky. We're going to get to the second part of the course to the story of spontaneous symmetry breaking. Before spontaneous symmetry breaking, electroweak symmetry breaking in the early universe, there was no massless mode. There was no photon. And it was just a SU2, which doesn't have a perfect messenger, which meant that there is no photo of the universe. There is no image of the universe from that time. The very first image of the universe was released at the time of CMB, cosmic microwave background, 300,000 years after Big Bang. That is the moment that the temperature dropped so much that spontaneous symmetry breaking happens. We're going to go through that at some point. But that's the moment the photon was released. Since then, we look at cosmic microwave background, we know that's a photo of the universe. That's the first image of the universe. Before that, there wasn't a massless mode, so we couldn't have an image. All right, that's just a rant on the side. Any questions so far? The punchline I want you guys to remember is Yang-Mills theory. Yang-Mills Lagrangian. So even though we wrote a term that looks like a kinetic term, it had interactions in it. But the form of the interactions are very, very fixed. This is very important. They are decided by the group theory. As opposed to scalar field, where you could just throw out whatever action potential you wanted, here you're not free. Group theory tells you what are the actions. What's the action? What is the form of the interactions? All right. Here's my last slide. So standard model particle physics, the picture of the universe as we understand. There are four forces: gravity, electromagnetism, weak and strong. Let's put gravity force aside because standard model is not concerned with it. You have electromagnetism. The force is a gauge field. Actually, let me just summarize it for you. All three of them are gauge fields. The particle for electromagnet is photon. The gauge group is U1. Weak nuclear force, there are three particles. It's SU2, and they're called W plus minus Z boson. Can anyone say why 3?
Generator of SU2
Exactly.
is
Adjoint.
three.
Adjoint representation. So in the case of QCD, it's SU3 and gluons. You know exactly how many gluons there we have.
8.
Yeah. That's the number of generators of SU3. And we've discovered them all, and the terms are matching really. The thing that's super elegant, so what is the symmetry group? All forces, gravity aside, all forces of nature are described using the following gauge symmetry group. That's it. U1, not SU1, U1. This is the symmetry group, the gauge symmetry group of Stanimal. It forces for you all the self-interact, it fixes for you all the gauge boson, their properties and their self-interaction. Right? Well, I haven't told you why these are all bosons, but that's another obvious thing actually about quantum field. We're talking classical field theory so far. So Yang-Mills theory is not just some fascination of theorists, it describes nature. It's as real as it gets. And a question for you guys to think about is gravity also a gauge theory? Is the other force that we're dealing with also a gauge theory? All right, any questions? This is the last lecture. This is the last slide of the lecture. We have a few minutes to discuss all the questions you may have. Okay, so if there are no questions, let me just say a few words about where I'm going, because I made this change recently with the remainder of the gauge discussion, section 4. In the next lecture, I will tell you guys a little bit about what are these non-localities in more concrete terms. They're called Wilson loops, and they're observables every time your algebra is non-trivial. Your topology is non-trivial. To explain that a little bit, I will use a different, so this is going to be important. I'll use a different definition of locality. It's intimately tied. I shouldn't call it different. Another definition of locality that we'll discuss, and you'll see that definition is sometimes very convenient. The other definition is sometimes convenient, right? It's a definition that doesn't rely on Lagrangians. And then we're going to say why are they not local? And then there will be another lecture. So we're going to describe also the geometry behind this. Why is covariant derivative natural? Why was this something that Yang-Mills guessed this as mathematicians? It's something supernatural. And then we'll get to the fact that, remember at some point early in this course, I promised that all quantum field theories that we discussed could be fundamental theories, or they could emerge in the infrared. So you might ask me, what the hell, how could, so the evidence for photon is some sort of high energy thing. How could you have gauge theories emerge in the infrared, in the continuum limit? And I'll describe to you guys that, as a matter of fact, gauge theories are very, very natural in the infrared. You should expect them. They do emerge all the time. And there's a beautiful physics associated with topological phases of matter associated that's related to this, and higher form symmetries and all that. This is more recent developments in the past 20 years. So I decided to add that to it because some of you guys might be interested in topological phases. All right. Any last questions?
I'm not too familiar with the Aharonov-Bohm effect. So are there any good resources I can study it from?
Yes, start with Wikipedia. If you want more, look up I think Griffith, Advanced Quantum Mechanics of Griffith has it. If you want more, or look up Jackson. I mean, that's something that people usually discuss in advanced quantum mechanics if they haven't discussed it. Jackson usually does, or some other places. But usually for these kind of things, if you haven't seen it, you know enough physics, Wikipedia and a bunch of references in there will get you there.
Okay.
But
Thank you.
hopefully the physics is very clear. The physics is I described to you. It's an example that demonstrates the following principle. The principle is this: that it's a quantum phenomena where you observe a phase. There is an observable, that's just a phase, coming from the movement of a particle in a region of space where the potential is constant everywhere in that region. So that means that because electric and magnetic fields have to do with derivatives and curls and of the potential, it just means that the electric and magnetic fields are zero. The potential is non-zero, but it has some observable consequences. Of course, there's topology in there as well. All right, last question. All right, if not, thank you so much. I will post problems. So now there's a new problem set, or I decided to split the problem set in two. So there will be a new problem set that I'll post, and it's always due 2 weeks after it's posted. So if I'm late a few days, well, the due date will move as well. Thank you so much, guys.
Thank
Bye.
you.